All right, I'm super excited about this lesson. We're Unit 5, Lesson 4, and it's over factoring polynomials. Now, the cool thing about this lesson is that it is mostly review, okay? And hopefully, because we're factoring, a lot of these sections should feel very familiar to you. You should be very confident in a lot of your factoring abilities by now. We will have two new types of factoring that are very similar in this lesson though. So when we get to sum of cubes and difference of cubes, you really need to pay attention to those parts because they are new types of factoring that you have never seen before. And they will be on your homework today. But starting off with factoring a polynomial by a greatest common factor. Okay, this part is something that you have all been doing this year. So remember, when we factor by greatest common factor, we're taking this polynomial, a string of terms that are connected by plus signs and minus signs, and we're turning it back into a multiplication problem. So when we factor by taking out the greatest common factor, we are going to use our inverse operation of division to turn this back into a multiplication problem. So remember, for this type, I usually start with drawing a line underneath the problem or our polynomial, and then I'm looking for the largest number that goes into my coefficients. So what's the largest number that goes into 12 and 10? That would be 2. And then I check my variables, and I'm trying to take out the largest or greatest amount that they have in common. So a's are common to both of these factors, and a cubed means 12 has 3a's, and a squared means there are 2a's. So the most that they can both give are 2a's, or a squared, we will call it. So 2a squared is the GCF, and now we're going to divide it out of each term. 12a cubed divided by 2a squared is 6a. Then my second term, 10a squared divided by 2a squared is just positive 5 because we divide our coefficients. 10 divided by 2 is 5. A squared take away a squared is no a's left. Now this part always gets wrapped up in parentheses, and we always put the GCF on the outside. Now this looks like a multiplication problem. It's distributive property. So we've done our job. It's been factored. The two factors are 2a squared and 6a plus 5. Okay, we'll do it again with number 2. We have our polynomial 14m to the 8th power n to the 5th minus 7m squared n squared. So we're going to divide out the largest number and the most amount of variables that we can, that they have in common. So the largest number that goes into 14 and 7 would be 7. And then I'm checking my variables. They both have m's. If we have 8 m's and 2 m's, the most that they can both give is m squared, or 2 m's. And then if we have n to the 5th and n squared, the most amount of n's we could give or take out of each is 2 n's. So we have a GCF of 7m squared n squared. And now we divide that GCF out of each term. So we start with our first term. 14 divided by 7 is 2. Subtract the amount of exponents. That's how we divide. That's our quotient rule for exponents. So 8m's take away 2m's is m to the 6th. 5n's take away 2n's is n cubed. All right, moving on to our second term. Now notice we have negative 7m squared n squared divided by its own self, 7m squared n squared. Anything divided by its own self is always the number 1, and this will be negative 1. So we wrap that part up in parentheses, and this GCF goes on the outside, 7m squared n squared. This has been factored by taking out a greatest common factor. Okay, in this next section, we are factoring by difference of squares. This is not new. We have been factoring with difference of squares. This is when we have this setup, of a squared minus b squared. So we have two perfect squares, a squared and b squared, represent that with a minus sign or a different sign in between. So variables are perfect squares if they have even exponents, 2, 4, 6, 8, and so forth. Numbers that are perfect squares, let's review those. So we'll make a list. We'll say 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100, 11 squared is 121, and so on. So our rule, remember, difference of squares isn't like figuring out a puzzle like our 1, 2, 3 factor tree. Difference of squares is like a set pattern of how we factor. And that pattern is, if we have our a squared minus b squared, the way it's factored is we always make two sets of parentheses. One gets a plus sign in the middle, the other gets a minus. And then because we're factoring undoes the polynomial, square rooting is the inverse operation of squareds. Okay, so if we have a squared, the square root of a squared is a, and that goes first in each set of parentheses if you remember. The square root of b squared is b, and that goes second. So our factoring is a plus b, a minus b as our setup. So on number 3, we have 9x squared minus 49y squared. Okay, 9, again, look at this. 9 is on our perfect squares list, and so is 49. X squared and y squared are obviously both perfect squares. So we're going to make two sets of parentheses. One gets a plus sign in the middle, the other gets a minus. My first term is 9x squared, so I'm taking the square root of that whole term, and the square root of that is 3x. 3x sticks together, but it goes first in each of our binomials because it was first in the problem. And then we're going to take the square root of our second term, not the negative part. Okay, again, the negative just means we're doing a difference of squares, and we have this set up. The square root of 49y squared is 7y. So we're going to put 7y second in each set. So this is like our setup of an a plus b, a minus b setup. But factored is 3x plus 7y times 3x minus 7y. All right, on number 4, if you're looking at this, obviously we are in the difference of squares section, but 72c4 minus 2, these two numbers that we have right now, none of them are on this perfect squares list. It's 2 or 72, neither one are on it. So do not forget that your first step of any type of factoring is always to check, is there a greatest common factor that can be divided out of our polynomial? And if you're looking at 72c to the 4th minus 2, you should be able to notice that they're both even. They can both be divided by 2. So that's our greatest common factor. We'll divide that out of each term. So what that gives us is 2 parentheses 36c to the 4th minus 1. Now what's so neat about this is this 36 and 1 are both on my perfect squares list. So now I truly can do a difference of squares factoring. So we'll bring down this 2 on the outside. The GCF just keeps staying on the outside of the equation as we factor more and more. Now I'll make two sets of parentheses. One gets a plus, one gets a minus. Then I look at my first grouping. It's 36c to the 4th. I take the square root of that whole thing. The square root of 36 is 6. The square root of c to the 4th. When we take the square root of exponents, we just divide them by 2. That's how you take the square root of exponents. So 4 divided by 2 is 2. So 6c squared is the square root, and it goes first in each set. And then we look at our second term. It was just the number 1, and the square root of 1 is 1. So we put that second in each set. So factored, this is 2, our GCF, times 6c plus 1 times 6c squared minus 1. Okay, number 5, we have 7m to the 7th n minus 28mn cubed. So I'm looking at this, and my brain is just telling me, it's like almost shouting at me that 7 and 28, like 7 can go into 28, and they both have m's and n's. So I see that they have all these things in common. So that tells me I need to divide out a greatest common factor first. So the largest number that goes into 7 and 28 is 7. Then I check my m's. We have 7 m's and 1 m, so we can take out the smaller of the two choices, which is 1 m. And then they both have n's. If we have 1 n and 3 n's, the most I can take out is 1 n. So 7mn needs to be divided out as a GCF before we can do difference of squares. And again, trying to do difference of squares with this original polynomial won't work because you can't take the square root of 7 or 28 or odd variables. So let's put our GCF 7mn on the outside, and let's divide. 7m to the 7th n gives us 1, and then m to the 6th, and no n's left. Minus 28 divided by 7 is 4. M, take away m is gone, n cubed take away an n is n squared. So now everything left inside this parentheses are perfect squares. Again, even exponents are perfect squares and 4 is a perfect square. So I'm going to bring down my GCF of 7mn, make 2 sets of parentheses because that's what we do for difference of squares. One gets a plus, one gets a minus. Now we take the square root of m to the 6. Well, 6 divided by 2 is 3. So square root of m to the 6 is m cubed. Put that first. The square root of 4n squared is 2n. So that goes second in each. So fully factored, this is 7mn times m cubed plus 2n times m cubed minus 2n. Okay, moving on to number 6. I've got 10w to the 5th power minus 10w. And you should notice right off the bat that they have lots of things in common. They're both the same number, that's common, and they both have w's. So let's take out a GCF. 10 goes into 10, and if we have 5 w's and 1 w, we can take out 1 w as our GCF. So that leaves us with 10w, the GCF on the outside, and then 10w to the 5th divided by 10w is w to the 4th. Then 10w divided by its own self, 10w, is minus 1. Okay, so we have 2 perfect squares with a minus sign in between. We'll do difference of squares. We have 10w, then 2 sets of parentheses. One gets a plus and one gets a minus. The square root of w to the 4th is w squared, so that goes in each set. The square root of 1 is 1. Now, this part's new. Okay, something new is happening. We haven't really seen this before. Okay, so hopefully you're paying attention. We are not done factoring. Sometimes you can apply difference of squares and factor it, but yeah, it could happen again. So 10w is fine. W squared plus 1 is also fine because of this plus sign. But w squared minus 1 is again 2 perfect squares with a minus sign in between. We can apply a difference of squares again, and this will happen one time on your homework today. So let's bring down what we already said was good, our 10w. And then we have our w squared plus 1. But this next section, again, that is circled, we need to make 2 sets of parentheses for it. One gets a plus, one gets a minus. And now doing our difference of squares, let's square root w squared. That's w. It goes in each set. The square root of 1 is 1. Now again, why could we do it to this one that's circled and not w squared plus 1? It's because it has to be a difference. Minus sign has to be between the 2 perfect squares. So it got factored again, just that piece. So this is fully factored. Again, be on the lookout for this part on your homework today. There will be a problem where you do your difference of squares and then that minus section one can have it happen again. So be on the lookout. All right, we are on sum of cubes. Now this is new. Please be listening. If you haven't been listening very much before now because it was all reviewed, this part is new. You have not done sum of cubes or the next section, difference of cubes. So you need to pay attention because this is a big part of your assignment today because it's a new type of factoring. Sum of cubes means you have 2 perfect cubes, an a cubed and a b cubed, and sum means we are adding them together. Okay, so let's talk about how we could recognize our perfect cubes. So let's make a little list here. You can use it as a reference. 1 to the 3rd power, or 1 cubed, is 1. 2 cubed, 2 times 2 times 2, that's 8. 3 cubed is 27. 4 cubed is 64. 5 cubed is 125. 6 cubed is 216. 7 cubed is 343. 8 cubed is 512. And we can just keep going on and on and on. But that's probably a good list for now. Now, if you see any of these numbers as part of the problem, and it's a binomial 2 terms, and your variables are also cubed or products of 3, like 3, 6, 9, 12, and so on, you probably have a sum of cubes factoring situation. And again, this is like difference of squares where it is a set pattern of how it is factored. There's not like a guesswork. It is always filling in a template or a pattern for the factorization. So here's our rule. If we have an a cubed, something cubed, plus another something cubed, we'll call it b cubed. This is how we factor. We have 1 set of parentheses that is just a plus b, we'll call it. So those are the cube roots of our original 2 terms. And then we have another set of parentheses, and this will be our a squared, and then it's minus, it's always a minus sign right here, a, b, and then plus our b value squared. Okay, again, the signs always go like this. Okay, it's very important that you have this written down correctly. It's always plus in the first set when it's a sum of cubes, and then it's a squared. It's always a minus sign no matter what in between the a squared and the ab, and then always plus your b squared. Again, this is always the rule for sum of cubes. So notice we're using these a's and b's, so we need to find out what the original a and b values are, which means like on number 7, if I have x cubed plus 27, okay, x cubed is obviously a perfect cubed because it's to the third power. 27 is on my perfect cubes list, so it's perfect cube. So what we need to do is find out what a and b, my original values, are equal to, because right now we have an a cubed and a b cubed. So how can you figure out what the original part is? We can cube root each of these terms. So we're taking the cube root of x cubed. So that means we do the exponent 3 divided by 3, which would be just x. So our a value for this template, for lack of a better word, is x. And then I'm taking the cube root of 27. And you can do this all on your calculator. Sometimes it's like the shift radical if you're using your Casio, but just take a minute to look and find it. Help each other out. The cube root of 27 means what number times its own self? 3 times made 27, and that is 3. So with this factoring, I'm going to write it down again down here actually. Again, I'm filling this in a plus b, and then a squared minus ab plus b squared. And I'm going to put x's in for my a's and 3's in for my b's. So my first set of parentheses, a plus b, would be x plus 3. And then I make my next set of parentheses. It says a squared. Well, a is x, so it's x squared. And then I put my minus sign, and then it's a times b. That would be x times 3, 3x. And then it's automatically a plus sign, and my b value squared. So 3 squared is 3 times 3, 9. And that's it. Again, find out what your a and b are by cube rooting your original 2 terms, and then fill them into this factoring pattern, and you're done. This is fully factored. There's never any extra factoring when you apply sum or difference of cubes, like we'll see in a minute. Okay, I know it's new, but stick with it. You're going to get it. Okay, number 8. I have m cubed plus 216n cubed. Okay, m cubed is perfect cubed. 216 is here on my list as a perfect cubed, and n cubed is perfect cube. So let's find out what our a value is and our b value is. So we find that by cube rooting these original terms. So I'm going to cube root m cubed. That is m. I'm going to cube root the whole thing of 216n cubed. The cube root of 216 is 6, and the cube root of the n cubed is n. So a is equal to m, and b is 6n as a grouping. So let's go ahead and, again, remember that this factoring goes a plus b, then a squared minus a times b plus b squared. And we'll fill this all in. So my a plus my b will be m, this is an equal sign, plus 6n. So m plus 6n represents a plus b. And then my a value squared goes next. So that would be m squared, because that was a. Minus sign. A times b is m times 6n. So remember to go alphabetical when you write your variables. 6mn. Plus sign, and then our b value squared. b is 6n. So 6n is being squared as a grouping. So square the number and square the variable. 6 squared is 36, and then the n is also squared. So this is fully factored for our sum of cubes. It's m plus 6n times m squared minus 6mn plus 36n squared. And that's all done. Again, I kind of like it. It's like almost filling in for a formula by doing this type of factoring. Okay, now number 9 and number 10, we're going to just step this up a little bit. I'm looking at number 9. We have 500a cubed plus 4. So I can see my variables cubed, and again, this is in the sum of cubes section, so it's leading me to want to do the sum of cubes factoring. But if you notice, 504, those numbers are not on our perfect cubes list. So don't forget, greatest common factor, you guys don't love it, but it can show up anywhere, anytime. So we always have to check for it first. The biggest number that goes into 504 is the number 4. So we're going to divide that out first. So that leaves us with 400, and then parentheses, we get 500a cubed divided by 4 is 125a cubed, plus 4 divided by 4 is 1. Now the great thing about this is that 125 and 1 are both perfect cubes. So now I can figure out what my a and my b values are. Okay, a is the cube root of 125a cubed, which is 5a. Again, use your calculator if you're not familiar with your cubes, but it does have to have that little 3 on the outside of the radical. And then I take the cube root of 1, which is 1. So b is 1. So now I'm filling in my a plus b, and you don't have to write this down. I'm just writing it down to kind of show how it all matches up like a formula. A squared minus ab plus b squared. So that will be a plus b is 5a plus 1. A squared is 5a, all being squared. So 5a times 5a, which is 25a squared, minus a times b. 5a times 1 is just 5a. And then plus sign, and our b value squared is 1 squared, which is 1. So fully factored, this is 5a plus 1 times 25a squared minus 5a plus 1. Okay, and then number 10, we have 24c to the 4th d plus 375c d to the 4th. And I'm looking at this, I don't recognize any perfect cubes yet, so I'm got to think, what's the biggest number and how many variables do they have in common? So I'm looking at 24 and 375, and the biggest number that goes into 24 and 375 is 3. And then they both have c's. We have 4 c's and 1 c, we can take out 1 c. We have 1 d and 4 d's, we can take out 1 d. So 3cd is a GCF. We're going to divide that out of each term first. So 3cd, and then 24 divided by 3 is 8. We lose 1c and 1d, so we're left with c cubed. And then plus 375 divided by 3 is 125. If we take out 1c and 1d, we are left with d cubed. Okay, good, I like this. 8 and 125 are both perfect cubes, and obviously my variables are cubed. So we'll do our sum of cubes, which again will be a plus b. It's a squared minus ab plus b squared. So a plus b, oh, I didn't show you what those are. Hopefully you were paying attention and you caught it. What are my a and my b values? Okay, a is the cube root of my 8c squared, which is 2c. B is the cube root of my second term. So the cube root of 125 is 5, and then we'll have 1d. So we're using 2c and 5d. So a plus b is 2c plus 5d. And then we have our a value squared. Again, don't just like square the number or the letter, you're squaring both. 2c times 2c is 4c squared. Minus sign, a times b is 2c times 5d, which would be 10cd. Plus sign, 5d squared means 5d times 5d, 25d squared. Close it up, and we're done. Okay, now in this section, the last part of this page of the notes, we have difference of cubes. Ooh, I was trying to circle it. Difference of cubes. Also, this is new. Okay, it's very similar to sum of cubes, but we have a little bit different rule or a little bit different formula for how it's factored. And again, it's determined by the sign in between these two perfect squares. So the rule is, if we have a cubed minus b cubed, or two perfect cubes being subtracted, is what that means. Here's how we factor it. We say we have the cube root of each of these things, a and b, but they're being subtracted. Now the cool thing is, and this is how I remember it, is if it's difference of cubes, my first set of parentheses, that binomial has a minus sign in it. When we did sum of cubes, my binomial to begin with had a plus sign to start. So it kind of matches. The same sign matches the type of factoring that we're doing for that first set of parentheses. And then it's still a squared, and then we say plus a times b plus b squared. Okay, can you see how this is almost exactly the same as our sum of cubes? We just changed where the minus sign was at. So I'm going to take a second. So this is difference of cubes, and I'm going to write up here for the sum. Look how it was so close. It was a plus b, then a squared minus ab plus b squared. So if you're noticing, each of these types of factoring only has one minus sign in it. For sum of cubes, it goes first in the second binomial, or it's like the second sign. But in difference of cubes, it is first. Okay, so just pay attention. Use your notes at first to help you. We're going to follow the same rule as what we did before. We need to know what a and b are, so we have to cube root each of these terms. So in 11, we have x cubed minus 1. So again, we're using our difference of cubed formula for factoring. So let's figure out what our a and our b values are. The cube root of x cubed is just x, right? Because we do 3 divided by 3 gives us 1, so 1x. The cube root of 1 is 1. So a is equal to x and b is equal to 1. So we're filling in a minus b times a squared plus ab plus b squared. That's our formula for factoring difference of cubes. So a minus b will be x minus 1. A squared would be x squared because x is a, plus sign because of this type of factoring. A times b is 1 times x, which is 1x. You can put the 1 if it makes you happy in front of the x. Plus sign again, and the signs all have to be exactly what this formula says. B squared is 1 squared, which is 1. Now there's no extra factoring that's ever done when it's sum or difference of cubes. However you fill in this formula is the full factorization, and you're done. Okay, number 12. We have 216k cubed minus 125. So I'm looking at my cubes list, I can see 216 and 125 are both perfect cubes. So I'm going to figure out my a and b right away. The cube root of 216k cubed, okay, the cube root of 216 is 6. The cube root of k cubed is k. And then the cube root of just the 125, don't put that negative sign underneath, but the cube root of 125 is 5. All right, so a is 6k, b is 5. And then if you look over here at our formula, this is what we're filling in for. First, we have a minus b in our first set of parentheses. So that's 6k minus 5. Then we make our new set of parentheses. It's our a value squared. So a is that whole thing, 6k. So think 6k times its own self. That's what squared means. 6k times 6k is 36k squared. Plus sign, because we're filling in this formula. A times b is 6k times 5, 30k. Plus sign again. Our b value squared is 5 squared. 5 squared is 25. Okay, so we have our factoring all filled in. We have 6k minus 5 times 36k squared plus 30k plus 25. Okay, number 13, we have 4 minus 32h cubed. Hopefully you're looking at your sum or difference of cubes, like those perfect cubes that we made at the where it said sum of cubes. And 4 and 32, neither one of those numbers is a perfect cube. But I look at 4 and 32, and I know that 4 does divide into 32. So that tells me there's a greatest common factor. So we have to always divide greatest common factors out of our polynomials before we apply another type of factoring. So let's divide each of these by 4. They don't have any variables in common, so our GCF is just a number. 4 divided by 4 is 1, minus sign. 32h cubed divided by 4 is 8h cubed. And again, I like this because 1 and 8 are both perfect cubes. So again, let's find out what a equals and what b equals. We're going to take the cube root of 1 to get our a value, and that is 1. The cube root of 8h cubed is 2h. Again, why am I cube rooting these? Because these are cubes, and when we factor, we go back to the original value. So cube roots undo perfect cubes. Now we're filling in this type of factoring. Again, the formula is a minus b, and then a squared plus ab minus b squared. So what would that look like? A minus b will be 1 minus 2h. Parenthesis, our a value squared, 1 squared is 1, plus sign. A times b is 1 times 2h for 2h. And then, oh, sorry, that's a plus sign right there. Hopefully you caught that, guys. I'm sure you're paying super good attention. And then plus our b value squared is 2h times 2h, 4h squared. And that's finished up. Good job. Okay, one more like this. And then on the back, we kind of have some more review types of factoring. Okay, 14, we have 2x cubed minus 54y cubed. Again, I'm looking at 2 and 54. They're not on my perfect cubes list, but I can see that they're both even, so I can divide out a GCF, and that will be 2. We don't have common variables, so the GCF is just 2. So 2 parentheses, 2x cubed divided by 2 is x cubed. Negative 54y cubed divided by 2 is negative 27y cubed. All right, so now I've got 2 perfect cubed inside those parentheses. So let's find out what a and b equal. A is the cube root of our first term. The cube root of x cubed is just an x. The cube root of 27y cubed is 3y. So again, look over here at this formula that's written on this screen. First, I have a minus b. So a is x, b is 3y. That's x minus 3y. Parentheses, a squared is our x value squared. Plus sign, a times b is x times 3y, so 3xy. And then our b value squared is 3y times 3y for 9y squared. So this is our factoring. So when you, my advice to you when doing this Excel assignment is really pay attention to whether you have a plus sign in between your two terms or a minus sign in between your terms. Okay, and that will help you know which formula, the sum of cubes factoring or the difference of cubes formula that you're supposed to apply. Keep your notes out and really pay attention to the structure of it until you get the hang of it. And then I bet you'll catch on and get it memorized super fast. Okay, our next section here on the back, starting with 15 and going through 20, we are factoring trinomials. So remember, tri means 3, so we will have a 1, 2, 3 factor tree situation. But you'll notice there are some little twists on this one. So pay attention to these differences. On number 15, we have n to the 4th plus 2n squared minus 24. Now, normally we start with a squared, and then we have our middle term as a regular, like n or x term, and then our constant, and then we do our 1, 2, 3 factor tree. But you can still do 1, 2, 3 factor tree if your exponents are like how they start on number 4, where our first term is to the 4th power, our middle term is squared, and then a constant. So 1, 2, 3 factor tree will still work on here, and then we'll go from there. So to factor this, we're looking for 1, 2, 3, a factor tree for negative 24. The two numbers multiply to negative 24 and subtract to 2. Those two numbers will be positive 6 and negative 4. So now remember, you're always breaking apart your first term. So when you break apart an n to the 4th, like evenly, we have an n squared and an n squared. So this is going to be n squared plus 6, n squared minus 4. Now when we have a normal trinomial, we're usually done at this point. But you always need to look back. If you have, after you factored something that's squared, okay, inside your parentheses, you might be able to factor one of those binomials again. And it will never be the one with the plus sign. It will be the one that has a minus sign in the middle. So this n squared minus 4 can be factored again because it is a difference of square situation. N squared and 4 are both perfect squares, and there's a minus sign in between. So I'm going to bring down my n squared plus 6 because it cannot be factored anymore. But for the n squared minus 4, I'm going to make two sets of parentheses. For difference of squares, we do one gets a plus, one gets a minus. The square root of n squared is n, so we put n first in each, and the square root of 4 is 2. So fully factored, we have n squared plus 6, n plus 2, n minus 2. Okay. Now number 16 is a little bit different too. We have w cubed plus w squared minus 20w. We do have 1, 2, 3. But our last term right here, 20, has a w attached. So we can't do our factor tree with that. If you notice, they all have a w. So we're going to take w out as a GCF first. Otherwise, we cannot factor it. So it goes w and then parentheses w squared plus 1w minus 20. Just 1w is removed from each term. Now my negative 20 does not have a w, and we go squared, regular w, constant. So we are set up to do 1, 2, 3 factor tree. What multiplies to negative 20 and subtracts to positive 1 will be positive 5 and negative 4. So fully factored, we're going to bring down the w that was the GCF, and then it's w plus 5 and w minus 4. Now some of you might think we can factor this one again, but we cannot. Notice our w's, neither of them are squared. We only do difference of squares if they're both squared. So this w minus 4 kind of looks like that n squared minus 4 that we factored extra, but because there's no squareds on the exponents, there's no other factoring we can do. Okay, on 17 we have 2a cubed plus 38a squared plus 68a. It is a trinomial, so we want to do a factor tree, but we've got the 2 in front of our a value. It's our leading coefficient, so we need to get rid of it. And then I notice they each have an a. So we're going to take a GCF of 2a out of each term, and that leaves us with 2a on the outside, and then a squared plus 38 divided by 2 is 19, and then 1a now, and 68a divided by 2a is 34. Okay, so now that we've divided out that GCF, we are set up to do 1, 2, 3 factor tree. What multiplies to 34 and adds to 19? Those two numbers are 17 and 2. So bring down your 2a as your GCF. It will be a plus 17 times a plus 2. Now why are these regular a's instead of a squareds? Again, because we started with an a squared and we broke it apart and put 1 in each set of parentheses to factor it. Okay, number 18, x to the 5th minus 24x squared minus 25x. Okay, looking at what they all have in common, they all have x's. There's no number in front of x to the 5th, so we can't take a number out as well. So the GCF is x. So put x on the outside, and we're left with x to the 4th minus 24x squared minus 25. Okay, so we go 4th power squared and then our constant. So we can still do our 1, 2, 3 factor tree. What multiplies to negative 25 and subtracts to negative 24. Okay, that will be 1 minus 25. So we'll bring down the GCF of x. And because this is an x to the 4th power, when we break it apart, we're putting x squared first in each of the parentheses. So x squared plus 1, x squared minus 25. Now because I still have my x squareds in the parentheses, okay, these two are done. Okay, you can't factor in x anymore. X squared plus 1, because there's a plus sign in the middle, we cannot factor anymore. But this x squared minus 25 is a difference of squares. Okay, two perfect squares with a minus sign in between. So this part gets the two sets of parentheses. One is plus, one is minus. The square root of x squared is x. The square root of 25 is 5. So it becomes x plus 5, x minus 5. And then we just bring down everything else because it does not change. So x squared plus 1. Don't you love that we've just stepped up our factoring skills a little bit? I do. Okay, on number 19, we have 3x to the 4th plus 14x squared minus 5. Okay, so I have a 3 in front of my x to the 4th power. And again, I can still apply my 1, 2, 3 factor tree to this. It still fits those given situations or criteria. But I have a 3 in front of my x to the 4th. We can't do factor tree still if there's a leading coefficient other than 1. So I check my other coefficients, 14 and 5. 3 does not divide evenly into any of those, so this is a slider. We're going to slide 3 and multiply it to negative 5. So we have x to the 4th plus 14x squared, and 3 times negative 5 is negative 15. Okay, now we can do our 1, 2, 3 factor tree. What multiplies to negative 15 and subtracts to 14 will be 15 minus 1. So when we put this in. Because this was an x to the fourth, we'll have x squared plus 15 and x squared minus 1. Now, it might look like we need to factor this some more, but don't forget, if we slide, we have to divide. We divide each of these factors by the slider first. So they're each getting divided by 3. We simplify. 15 divided by 3 is 5. 1 over 3 does not simplify, so 3 goes bottoms up. So we are now left with x squared plus 5 and 3x squared minus 1. Okay, and 3x squared is not a perfect square because of that 3. Okay, because of this 3 in front of x squared, not a perfect square, we cannot do any extra factoring. It's done. Okay, to finish up, we're going to do a couple of these examples and review how to factor by grouping. We did go over this when we did our factoring review at the beginning of the semester. Factoring by grouping only happens when there are 4 terms in the polynomial. Okay, so your first step over here, it says group the first 2 terms together and the last 2 terms. So I always showed that by cutting them in half. Make 2 groups, 2 on either side. And then it says factor the GCF out for each group. So I'll draw a line underneath each and I'll take out a GCF. Now each GCF will be different because each grouping is different. For x cubed plus x squared, they have x or squared in common, or 2 x's. So we're going to divide out an x squared. Okay, that leaves us with an x squared on the outside, and then 1x, if we have x cubed, take away x squared, plus x squared divided by x squared is 1. Okay, that's what we get when we divide out x squared from each term as a GCF. And then I have negative 4x minus 4. Okay, the greatest common factor, 4 goes into both of them. But again, if your first term in your grouping is ever negative, you make your GCF negative. Otherwise, things don't match up right in the end. So I'll say the GCF is negative 4. When we divide each of these terms by negative 4, we get a positive x. Negative 4 divided by negative 4 is positive 1. Wrap it up, and negative 4 goes on the outside. So the awesome thing about factoring by grouping is after you've divided a GCF out of each group, what's inside the parentheses always matches if you've done it correctly. Because it's exactly the same, it does not mean x plus 1 squared. The matching just means we did our job right for this type of factoring, if you recall. So x plus 1 is only used one time. It's one of the factors. The other factor is made up by the 2 GCFs. Remember I said they kind of hook up, they get married, and form a happy little binomial. They are x squared minus 4. Oh, but we are not done. And I'm just seeing this too. Look, x squared minus 4. I'm like, okay, something still has an x squared and a minus sign, so I'm checking this number. 4 is a perfect square. So we're going to do difference of squares just for the x squared minus 4. So 2 sets of parentheses, one gets plus, one's minus. The square root of x squared is x. The square root of 4 is 2. So this turns into x plus 2, x minus 2. So again, sometimes our binomials can just be factored again. And then bring down the factor of x plus 1. And now it's done. All right, number 21, we have x cubed minus x squared plus 9x minus 9. We have these 4 terms. We're going to cut it in half. We're going to go back and we're going to find a GCF and divide it out for each grouping. For x cubed minus x squared, our GCF is x squared. That's how many x's I can pull from each. So x cubed, take away x squared is 1x. X squared divided by x squared is minus 1. Wrap it up. X squared's on the outside. For my next grouping, 9x minus 9. Okay, the GCF is 9. It goes into both those numbers. No x's because they don't both have them. So 9x divided by 9 is x. Negative 9 divided by 9 is negative 1. Wrap it up. And this is a positive 9, so we put plus 9. So because we check our parentheses, they match. That means we're doing it right. And so we bring down x minus 1 only one time. And then my other binomial is for x squared plus 9. Now this cannot be factored anymore because even though we have an x squared and a 9 that are both perfect squares, there's a plus sign in between. It has to be a difference of squares to do it more. So it's finished. And we'll call 22 our last example. K cubed plus 5k squared minus k minus 5. Cut it in half. Looking at k cubed and plus 5k squared, the most they can both give is a k squared. K cubed, take out a k squared, is 1k. 5k squared divided by k squared is just a positive 5. Wrap it up, k squared on the outside. My second group is negative k minus 5. Might not look like they have anything in common, but because there's this negative in front, if I just brought it down as it was, it wouldn't match up with this k plus 5. So again, that's negative that I have the arrow on always means we at least have to divide by a negative, so negative 1. Dividing these by negative 1 gives us a positive k plus 5. Wrap it up, negative 1 goes on the outside. Now that was great because now these two terms in the parentheses are identical. So we have done it correctly so far. We bring k plus 5 down one time for our answer. K squared minus 1, they hook up. Oh, but then hopefully you guys all noticed it before I even said it. K squared minus 1 can get that extra factoring that we're going to start noticing happening a lot more. K squared and 1 are both perfect squares, and we've got a minus sign in between. So difference of squares. Two sets of parentheses, one gets plus, one's minus. The square root of k squared is k. The square root of 1 is 1. So it turned into k plus 1, k minus 1, and then bring down the k plus 5. All right. You guys got all the information you need to do your homework. Good luck.